Everyone, my name is Anusha, and alongside my teammates,
Barani,
I'm good.
Andrew,
Gordon.
Steve.
Thank you.
we will be presenting our research project, GLEAM. The digital realm faces a multitude of threats from malware, viruses, worms, trojans, ransomware, spyware, and more. Conventionally, pattern recognition has been employed for malware detection, yet it falls short against new and evolving strengths. So we leverage generative adversarial networks and large language models. These technologies collaborate to craft lifelike synthetic malware samples. This aided us in comprehending and countering emerging threats.
to understand our overall project, you will need to know about GANs. GANs stand for Generative Adversarial Networks. It consists of two neural networks, a discriminator and a generator. They use a feedback loop where the discriminator tries to classify between the generated data and the input data. And depending on the loss, it feeds back into the generator until genuine and generated samples are nearly indistinguishable. Traditionally, GANs are used for images, so we made use of tabular GANs with our malicious samples. On the right-hand side, you can see a diagram of how a GAN looks like. As I mentioned earlier, the feedback loop uses a discriminator and a generator, and it feeds the feedback into the generator. And in the end, it's a coin flip, and the genuine and generated samples are nearly indistinguishable.
So some malware basics. So malware is basically code that causes or is aimed towards causing a malicious action. Some famous examples are Trojans and ransomware, and it aims to disrupt operating system operations, most usually by locking users out of the operating system. A notorious ransomware attack is the WannaCry attack, which occurred in 2017, in which global computers that used the Microsoft Windows OS were infected, and the hackers locked users out of PCs and asked for ransom in the form of Bitcoin so that they could get back into their computers. Ransomware in recent years has evolved from a simple form of cybercrime to a multi-billion-dollar industry. And with synthetic malware generation, the objective is to test and create artificial malware for the purpose to test and enhance malware detection systems. We parse our raw data into two formats. The first one, which is shown in figure 2, is the hexadecimal representation of binaries. And the second, shown in figure 3, is assembly language source code. This facilitates the process of feature engineering and makes the data more meaningful.
in our research, we leveraged n-grams to extract features from both hexadecimal and assembly opcodes in benign PE files. These contiguous sequences helped us capture crucial file traits. By extracting n-grams, we aim to create a robust representation that would effectively mask any malicious data, allowing us to focus on discerning legitimate patterns and structures. Our next step involved standardizing PE files into hexadecimal representations to ensure a consistent format for analysis. By merging n-grams with the LLMs, we were able to predict and generate data sequences, further supporting our ability to identify potential irregularities or anomalies in the files. Another large aspect of our method involved enhancing GANs, and through our augmentation techniques, we aim to boost the performance of GANs in the context of PE file generation. By incorporating the insights gained from our LLM and n-gram analyses, we were able to consistently improve the GAN's performance and predictive capabilities. Our work was built upon the PE malware machine learning dataset curated by Michael Lester and published by Practical Security Analytics, LLC. This dataset played a significant role in our analysis of evasive malware and our efforts to understand the complexities of PE files in both malicious and benign contexts. To comprehensively explore evasive malware, we needed access to labeled samples that could capture the intricacies of these malicious files. For this purpose, we sourced raw labeled PE files from our chosen dataset, which provided us with a diverse collection of PE files that encompassed various forms of malicious software. Our chosen dataset consists of a substantial collection of around 200,000 PE files. This dataset has a nearly balanced distribution with an almost equal split between malicious and benign files. This balance ensures that our analysis and subsequent conclusions were not skewed toward any particular category and rather a more accurate and unbiased representation of the data. Our approach involved the use of 5 distinct machine learning algorithms, collectively referred to as the black box detector, characterized by invisible internal parameters. Our 5 different algorithms were logistic regression, k-nearest neighbors, random forest, decision trees, and support vector machine. Logistic regression offers a robust way to model binary outcomes and is well suited for understanding the relationship between features and outcomes. GAN is useful for identifying clusters and can capture local patterns effectively. Random forest provides enhanced accuracy and reduced overfitting and is suitable for classification and regression tasks. Decision trees are interpretable and help reveal key points in the data. Finally, SVM is effective in high-dimensional spaces and can handle complex decision boundaries.
Our GAN makes full use of the features of benign data to camouflage the malware data. We extract n-grams from hexadecimals and opcodes that provide crucial information about the file, such as frequency and co-occurrence of character sequences. Specifically, we use 6 grams on hexadecimals and 2 grams on opcodes based on malware classification results from previous publications. This feature extraction is done with a simple Python program. We then combine an 800-dimensional malicious feature set with a 200-dimensional benign feature set. Lastly, we map each sample to the new 1000-dimensional vector and feed the resulting feature matrix into the generator. As you can see, we start with malicious and benign data in the form of hex codes and opcode n-grams. We then find the most revealing 800 malicious features and 200 benign features, and we take the logical OR operation of these 2 feature sets in order to create adversarial examples while maintaining malicious content. We feed the new feature matrix into the generator, which produces 1000-dimensional adversarial malware samples. These samples are then tested on the black box detector.
For our language model, we used a pre-trained model of GPT-3 from Hugging Face called GPT-Neo 1.3b. We chose this model because it is known for its text generation tasks. The input for our LLM were grayscale images of the hexadecimal samples. The samples used are ones that the classifiers had failed on detecting initially, which are all stored in a CSV file. The output for our LLM were hexadecimals that imitate both malicious and benign data. Our LLM utilized iterative generation, where a portion of text was presented to the language model and then generated additional segments of a hexadecimal data in return. In this diagram, you can see that our LLM starts off with grayscale hexadecimal images, which are split into 2 folders of benign and malicious data. These file names from a CSV detail which samples the classifiers had failed on, making those the input for our LLM. The LLM then produced synthetic benign and malicious hexadecimals in return. This diagram details the iterative generation that happens in our LLM. The initial hexadecimal goes through tokenization, where the hexadecimals are turned into text tokens. Then, after iterations, we're able to generate the hexadecimal. To determine how evasive our generated data was, we used benchmarks from the original dataset. By running our original data through the black box, we could see that these well-trained classifiers had produced a pretty high accuracy in all of the tests. Evasiveness refers to the ability of generated malware samples to evade detection by classifiers. Higher detection rate or accuracy meant that classifiers are able to correctly identify the synthetic malware samples, which means lower evasiveness. A lower detection rate or accuracy meant the synthetic malware samples are successfully evading detection, resulting in higher evasiveness. Both the LLM and the GAN were able to produce lower true positive rates than the original dataset in all cases, which means they successfully created samples that evade malware detection. For example, for the support vector machine, the true positive rate had dropped 34%, 93 to 59, when fed the LLM-generated data. Random forest, which had our highest true positive rate on the original dataset, had dropped 27% when fed the GAN-generated samples.
With our GLEAM model, we were able to make synthetic malware that can slip through machine learning detection models. The GAN had an average evasion rate of by 20.2%, and the LLM's average evasion rate was 25%. These results showcase the possibilities of expanded feature sources and even LLMs for adversarial examples. This experiment revealed the vulnerabilities in machine learning-based malware detection algorithms. We encourage further work in developing novel malware detection approaches, such as safe dynamic analysis of malware PEs. And now it's time for our Q&A.